Let's work a problem involving Newton's second law, otherwise known as F equals ma, where F is the total force, sometimes called the net force. M is the mass of the object that is subject to the net force, and A is acceleration. The system we'll look at is drawn here. We have a tabletop. On the tabletop is a 4 kilogram block. A string is attached to the block. It passes over a pulley. At the end of the string is a hanging mass, 3 kilograms. The tabletop is frictionless. We'll discuss friction later on in this chapter. Tabletop is frictionless, so the only force that can influence the motion of this object is the tension in the string. There's one tension, and it's the same everywhere along the length of the string. The tension, you may recall, in a string equals whatever force either end of the string exerts on what it's attached to. So this string is exerting a force to the right equal to the tension in the string, a force to the right on the 4 kilogram object. But at the other end of the string, the same force is applied to whatever is attached to that end. And that force points upward as far as the 3 kilogram mass is concerned, upward. And the force the string exerts on the 3 kilogram mass is a tension. Same number as back here. Well, the system, the pair of objects, is accelerating. The block is sliding to the right in the positive direction. It has a positive acceleration. Now, whatever this block is doing, but in a different direction. Whatever the speed of the block is there at any moment, it's the same as the speed of that block. Whatever the acceleration of the block is at any instant on the tabletop, same acceleration for this object, except this object's acceleration, while it'll be the same number as that object's acceleration, the same number, this acceleration, A, is a positive number because it's accelerating to the right in the positive direction. This object will be accelerating downward in the negative direction, so its acceleration will be a negative number. It will be the negative of whatever that positive acceleration A is. Consequently, we symbolize the acceleration of this block, of that hanging object, as negative A. A will be positive, and the negative sign makes that acceleration appropriately negative. So far, so good. Consult the diagram. There are two unknown quantities, a number of known quantities, the mass in two places, but there are two unknowns, one of which is the acceleration A value. The value of A is unknown, and the tension in the string is unknown. Two unknowns. In order to solve for those two unknowns, we need to make two equations. The first equation could come from, and will come from, because that's my choice, an application of Newton's second law to the 4 kilogram object. I'll tell you where the second equation will come from later. So, to apply Newton's second law to the 4 kilogram object, we draw a separate diagram which shows only the 4 kilogram object and whatever force or forces are acting on it. Such a diagram is called an isolation diagram. We're isolating the current object of our attention separate from the entire system. There's your isolation diagram. The only force that causes motion of the 4 kilogram object is a tension force acting to the right. There will be an acceleration A unknown a tension T unknown. The boxed equation is Newton's second law applied to the 4 kilogram object. F equals ma. F in F equals ma equation is the total force acting on the object of interest. The total force acting on that object is the tension. Any other forces cancel, such as the push up by the tabletop on the block is matched by the pull down by earth on the same block. Those forces cancel each other, ignore them. Total force then is just T, the tension unknown. It's equal to ma. M is 4. A is unknown. The boxed equation is good. Come back for it later. We need another equation. The other equation will come from an application of Newton's second law, again, F equals ma, to the other object, the hanging mass, which is shown here in an isolation diagram. 3 kilogram hanging object. String is attached to it, pulling upward, but not winning because the pull by the earth will be greater, it turns out. So the block will be moving downward. It will have, as we said earlier, an acceleration symbolized as negative a. I show here pull by earth, the so-called weight of this object, which is mg in magnitude, 3 times 9.8, m times g. We have to insert a negative sign there because that force points downward in the negative direction. This picture here will lead to an equation based on F equals ma up here. The left-hand side of this equality is the net force acting on the 3 kilogram object. One force is a tension force acting upward in the positive direction, and the other is the pull by earth, negative mg, negative 3 times 9.8. Right-hand side is ma. Mass is 3, acceleration expression is negative a. Solve this equation by substituting for the tension 4 times a. So we put to use the first equation that we made, substituting for the tension 4a. Bring the negative 3a over here to make 7 of them. Take that negative number over there to make it positive. Divide by 7. Final result for the acceleration, the value of a, is 4.2 meters per second squared. So far, what do we know? We know that the block on the tabletop is accelerating to the right with an acceleration of 4.20 meters per second squared, a positive number. The hanging block is accelerating downward with the same number, but a negative sign. Now let's get the tension. Simple matter. The tension we found earlier is 4 times whatever the acceleration is, and so here we go. T is 4 times that number. Final result is shown on the board. I hope what I showed you was clear. If not, rewind and replay it, or send me an email and I'll help you understand it better than you do.